everyone, and welcome to today's webinar, sCMOS Cameras for Scanning Light Sheet Microscopy. I'm Cassie Saltman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Teledyne Photometrics. To learn more, visit www.photometrics.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you're having trouble seeing or hearing the presentation. I'd like to now welcome today's speakers, Dr. Matthew Kose-Dunn, Content Manager, Teledyne Photometrics, and our guest speaker, Professor Reto Fiolka, UT Southwestern Medical Center, Texas. Matthew, you may now begin your portion of the presentation.
Brilliant. Hello, everybody. Thanks very much to
Hello
Cassie.
and welcome to another Teledyne Photometrics webinar with me, Dr. Matthew Kose-Dunn, featuring guest speaker, Professor Reto Fiolka from UT Southwestern Medical Center, Texas. This webinar is all about sCMOS cameras for scanning light sheet. If you'd like to learn more about light sheet, I have previously done a webinar concerning light sheet basics and static light sheet in June of 2022. If you'd want to hear more about this and get a general overview of the technique, then that webinar is available on demand from LabRoots or from the webinar page of the Photometrics website. Firstly, a little bit about Teledyne Photometrics itself. We design and manufacture high-end cameras for scientific imaging, from imaging cells and organs and materials and galaxies. Our camera solutions support demanding quantitative scientific research, and we're the market leader for scientific CMOS camera technology. The company has a lot of pedigree, having been around for nearly 50 years and part of the Teledyne Imaging Group since 2019. A little bit about the two speakers on today's webinar. The first is myself, Dr. Matthew Kose-Dunn. I'm a marketing and content manager at Teledyne Photometrics, and I bring you these webinars and all sorts of other content on our website, www.photometrics.com. However, the main focus here is our guest speaker, Professor Reto Fiolka of UT Southwestern Medical Center, Texas. One of Professor Fiolka's focuses is on the development of novel microscopes and imaging techniques, with an aim to perform more physiologically relevant imaging by extending the current capabilities of optical microscopy by improving spatiotemporal resolution and optical penetration depth. All of this work represents big steps forward for getting more detailed live cell imaging in realistic 3D environments. But before we get into all that, let's go back to basics. The aims of light sheet as an imaging technique are numerous, including minimizing photo damage and bleaching and the resultant cell toxicity, avoiding out-of-focus light in order to improve image quality, granting optional sectioning capabilities, which allows free imaging of large 3D samples, implementing high-speed imaging in order to image fast dynamics such as calcium or voltage imaging over long experimental timeframes. And with light sheet, anyone familiar will know that the technique is very flexible and there are hundreds of variants of light sheets that can target specific imaging needs in order to answer specific scientific research questions. Light sheet is one of those techniques with so many variants, sometimes we run out of letters of the alphabet for naming acronyms. Essentially, light sheet holds a lot of promise and is a rapidly developing field for this reason. And most of the aims of light sheet are achieved by the way that illumination and detection are treated differently when compared to typical wide field imaging. This diagram here shows a typical light sheet setup, where illumination takes the form of an hourglass-shaped sheet of light, hence the name light sheet. By imaging our small cylindrical sample here with the thinnest part of the waist, the beam waist of the light sheet, we can achieve high-resolution imaging only in the section the sheet is illuminating, which achieves an effect similar to confocal microscopy, where instead of bathing the whole sample in light and looking at the excitation from a single plane, we can illuminate and detect from a similar plane, reducing the illumination and photo damage to the remainder of the sample. The objective seen here is being used for detection, So illumination is occurring at 90 degrees perpendicular. This is a classic format for light sheet, but the light sheet itself can be shaped in many different ways, and the sample geometry can be changed, the angles of the detectors, the number of detectors, all sorts of things can be changed. But the focus of this webinar is the change of having not just a single static light sheet, but to have a light sheet that can be moved or scanned across the sample. Why would we wish to scan the light sheet across the sample? Well, as mentioned earlier, light sheets only illuminate a small region of the sample, and for higher image resolutions, you need thinner light sheets. The thinner the light sheet, the less of the sample that receives the illumination, the less of the sample that you're able to image. In addition, static light sheet only illuminates the sample in one direction if using one light sheet, for example, from left to right. And this can cause shadows and artifacts due to this non-uniform illumination. This issue can be resolved by rotating the sample itself or by using multiple illumination objectives, so using multiple light sheets from multiple directions. But this can lead to longer exposure times and increased photo damage, as well as potentially reducing sample geometry options if your sample has to be rotated. Another solution is to keep the sample in place, but instead move the light sheet. This is scanning light sheet. Here we can see a bit of an example of this. This is adapted from a 2018 publication. On the left is static spin. On the top you can see the classic hourglass shape of the light sheet in grey, and you can see the artifacts generated in the image as the light sheet propagates from left to right and causes these long purple shadows in the sample. With a technique known as digitally scanned light sheet, or DSLM, which uses more of a pencil beam which is then scanned through the sample, these additional illumination points greatly reduce the artifacts in our image. In scanning light sheet, rotating mirrors are typically used to scan the light sheet across the sample. The ways in which this can be done can vary, but we'll get onto that in the next section. Overall, there are some other immediate benefits to scanning light sheet, such as imaging being less affected by irregular 3D shapes. As you can tell from the rotating image we've got here, in general, biology is rarely neat, tidy, or symmetrical, so samples are typically irregular and lumpy. And with some scanning, this can have less of an impact on image quality. Scanning light sheet can also lead to higher contrast and more uniform resolution over a wider field of view. This improvement with large field of view imaging is very important for high content or high throughput imaging of many sample variations or repeats, or simply when imaging very large samples, like centimeter scale mouse organs, that kind of thing. However, the benefit of larger field of view light sheet is only realized if you pair this technique with a large field of view camera and a large field of view microscope, because the imaging system as a whole will be limited by whatever has the least spatial resolution or whatever has the smallest field of view. Speaking of cameras, if the scanning of the light sheet can be synchronized with the rolling shutter of the CMOS camera, it can act as a sort of confocal slit, rejecting background and improving contrast. And this kind of reduces the dark time and further improves imaging efficiency. Teledyne photometric CMOS cameras do have full advanced control over their rolling shutters, and this is known as programmable scan mode. We'll discuss that further into the webinar. In general, there are numerous imaging benefits to using scanning light sheet, but it's best to hear from a developer and user of these techniques. So at this point, I'll be handing over to our guest speaker, Professor Reto Fiolka.
Hello, everybody. My name is Reto Fiolka. I'm an assistant professor at UT Southwestern Medical Center in Dallas, Texas. And our work has been focusing on light sheet microscopy for the last roughly 10 years. And we also, of course, make use of advanced scientific cameras. So I can just talk a little bit about some basics of light sheet microscopy and where also camera technology comes in. In general, one can classify it in three ways of how a light sheet is generated. There is what we could call the static light sheet. They're also called SPIM, for selective plane illumination microscopy, where essentially a beam of light is shaped into a one-dimensional Gaussian beam waste. So it is instantaneously generating something that is close to a light sheet, and in blue here, and the fluorescence is detected in green, orthogonal to the optical axis of the system. Then a second technique that was introduced later was the digitally scanned light sheet, where you essentially focus a beam of light into something like a pencil of light or a two-dimensional focus, and you scan the beam laterally, and so in the time average, you create a light sheet. And we will see in a bit why that can be helpful. This also requires a bit more advanced cameras. Then lastly, this was the technique that came later, was the axially swept light sheet. So here, like the SPIM, you create instantaneously a light sheet, it's kind of a one-dimensional focus, and you sweep the light sheet in its propagation. So it's not in the X direction, it's essentially going in the Y direction, as one can see. So if you want, so it's like the ESLM, but it scans in an orthogonal direction. And we will see also in a bit why that can be useful. Since we were involved in the ASLM technology, we'll talk a little bit first about that. So imagine here, this is your light sheet in light blue. That's kind of the beam coming in. It forms a waste in dark blue and goes out again. And this lens here will be the imaging system, and below here will be a scientific CMOS camera. So if you sharply focus light sheet, it will also be relatively short. So on modern CMOS, you can cover a large field of views, but this light sheet would essentially only occupy a rather narrow strip because this beam waste is rather short. That's some of the trade-offs you have to do in light sheet. If you want a very thin light sheet, it tends to be rather short. And if you want to have one that covers, say, a large field of view, it will inevitably become much thicker. So the idea in the axially swept light sheet microscope is to essentially move the light sheet in its propagation direction, and then the fluorescence from the beam waste essentially swept over the camera. If you were just to do that in global shutter, then you would record the beam waste, but also the associated blur from where the light sheet is not in the beam waste. And so here, one thing that is very helpful of the CMOS technology is that you can have a sort of rolling shutter readout, so that essentially a row of pixels moves here from left to right, and that can be synchronized with the sweep of the light sheet. And there's not a single row of pixels, it's usually some 10 to 60 pixels wide strip, so that it not only covers the very center of the light sheet, but essentially what we call the confocal parameter, or the Rayleigh range, that is kind of the length of this sheet that is useful. This would not be easily doable with a CCD or older camera technology. Here we rely on the flexible readout. In principle, and that's where we're excited about latest cameras that might be in the pipeline in development, that can have multiple regions of interest in which you may do a selective readout. So this process could also, to a degree, be parallelized. So we have been working quite a bit. We call it the ASLM, the axially swept light sheet. And here this is a clear mouse brain with a certain population of neurons labeled method. And this is a top view, or a traditional XY view of a stack. And here is a cross-sectional view in ASLM. And if we zoom in, you can see with a normal light sheet, the Z resolution would be rather poor, because you would need a very long and thick light sheet to cover this field of view, which is in the order of 800 microns by 800 microns in this case. And with the ASLM, if you zoom in this region here, again, this is a cross-sectional view. So traditionally, the worst view in any microscope, you can still see fine details like these spines here. So in principle, you have isotropic resolution that way, so that you have essentially the same level of detail. And so that's why we're excited about the ASLM, and currently we see most of its use clear tissue imaging. That can be brain imaging, but can also be other organs or potentially even entire model organisms that you want to image with. There is no preferred orientation. There is not just one lateral plane where you want to have the high resolution. The spatial detail can be in any dimension. So the goal is to image millimeter cubed or even centimeter tissue volumes. It can be brain research, but we also involved in a cancer research, for example, to map metastatic sites in organs that have, cancer cells that metastasize there, and, for example, image at subcellular resolution what is the morphology of these cancer cells, what are certain pathways that may be activated, and distribution of signaling proteins. So that is one area, and why this is important is with tissue clearing, you can now essentially get optical access to really vast volumes of tissue, where normally light microscopy couldn't get beforehand, because light scattering would have prohibited from going to like millimeter or centimeter depths inside an organ. But when it's clear, you can. But if you were to image that with a confocal microscope and with maybe a microsecond dwell time, and in the confocal microscope you raster scan the volume, then the typical organ you would actually have to image for weeks to months. So literally you would have to book a confocal microscope for a good portion of the year to just image just once. And thanks to light sheet microscopy and the progress on cameras, so today's sCMOS can have multiple megapixel, so you record at the time millionfold parallelized, so you can in one exposure of the camera record millions of pixels, in contrast to the single pixel that the confocal microscope acquires. So very large volumes can now be acquired in a matter of hours to days instead of weeks to months, and so it becomes more tractable. So imagine if you wanted to study an Alzheimer model mouse that may have less synaptic connections. So if you were to image multiple mice or specific sections of the mouse brain, and you wanted to do 10 of each, the wild type and the one with the Alzheimer model, then you could, in principle, if you were to use a confocal, you would need to image for years, literally. And then with the light sheet microscopy, it becomes at least tractable in the sense of the time effort. The amount of data, of course, is a whole other question. So thanks in part to the amazing sCMOS revolution, so we can now have acquisition runs that fill tens to hundreds of terabytes. So we still have to grapple with how we store and process that wealth of data. Okay, so that is one part where we're working on the actually swept light sheet microscope, but I ought to maybe also talk a little bit about the DSLM, which has become an important technique in the field of light sheet microscopy. It's particularly suited for embryo imaging, or the samples that have still some degree of scattering. And what you can do here, this is a wonderful animation from Philip Keller's lab, one of the pioneers in DSLM, and one of the labs that pushes this technology further. You can also use a rolling shutter. So here you can see the kind of pencil beam is, or two-dimensional focus is scanned through the sample, and the fluorescent light, essentially a line, travels across the camera. And so if you also use a rolling shutter, then you get a bit of different effect than the ASLM. The ASLM just kept the beam waist within the active pixels. Here, you can make it a bit more narrow, because you essentially look along the beam that is propagating, and you get a little bit of a confocal effect. So you can reject some scattered light that may lie outside of the focus beam, and that can be very helpful when imaging scattering objects. And also here, I think with the advances, new camera technologies, if you can have multiple rolling shutters, this process obviously can also be parallelized. So one concern, or maybe one insight that was gained in a light sheet microscopy, namely by the group of Eric Betzig, was that, the lower you make the peak intensity, in many cases, the better you're off in terms of phototoxicity and also photobleaching, because many processes are not linear. So if you're hard pressed on photons, you do not want to use a single focus spot. Like in a confocal, a line is already better, but multiple lines that distribute the power more evenly, or in the time average, get maybe the same photon flux with a lower laser power would be better. So obviously also parallelizing this process could be helpful, and it could also lead to interesting acquisition schemes. This was a theoretical concept that we presented. So you could, if this were the detection objective and this the illumination objective, you could have an array of such, let's call them pencil beams or two-dimensional foci. And obviously, if you had multiple rolling shutters, you could have an array of these beams. If they were arranged in a single plane, that would already be great. That could lower phototoxicity. But in principle, you could also stagger them in height. So have each beam at a different focal distance to the detection objective. And hence, you could, as you sweep this array of beams across the x direction here, you could essentially span multiple light sheets, and the fluorescence arising from each light sheet could be recorded in individual rolling shutters. We did some proof of concept that was not actually having a camera with multiple regions of interest, but we essentially just had two light sheets or two-dimensional beams that were staggered and swept across, as shown before. And we essentially just read out for every position of the beam a whole image or a portion of the image, and then in a post-processing steps just selected the corresponding lines. And then indeed, in essentially with the two beams, you could record at the same time different portions of the cell. These are kind of a given position of these cancer cells, two different planes that were recorded. So without changing the focus or moving the sample, you could record two different planes. And then when a volume was acquired, the two volumes look very similar, but essentially when they're overlaid, they were recorded with kind of a different Z offset. So if they're overlaid, one can see in color, they were a little bit shifted. So different portions that were recorded. So sure, this was just a proof of concept because we didn't have an advanced camera at the time. But I think once the readout modalities of sCMOS may become a bit more flexible, then we could potentially do interesting things also with these concepts. That was just a very brief overview. We also do other things, develop new ways of launching the light sheets with a so-called single objective light sheet microscope, or they're also known as oblique plane microscopes or scape microscopes. So those are technologies that use a single high-NA lens to launch the light sheet and also detect the fluorescence light. That's an area where we also got active. We try to further combine light sheet microscopy with structural illumination microscopy. So structure, or short SIM. SIM is a technique that can double the resolution of a wide field microscope, non-phototoxic way. So there we also started a new research avenue But needless to say, all these techniques, they will benefit from advances in camera technology, like having bigger array sizes, more pixels, having faster read. I would say, in general, light sheet microscopy will directly benefit from such advances. I think in terms of speed, light sheet microscopy can be made very fast. So currently we can, if the sample is bright enough or the brightness of the label allows it, you can essentially run the maximum frame rate of the camera. Normally want large chip sizes, so having at least 2K by 2K pixels, or preferably more. We appreciate the 16-bit depths, so having a large dynamic range is helpful. In some application, we go to rather thin samples. We also appreciate low read noise, and well, dark noise is no longer that much of an issue on most cameras, but nevertheless, cooling of the camera is often desired. We also notice that sometimes when there is a fan on the camera, it can cause vibrations, so we prefer water cooling. Depending on the type of light sheet we're doing, we also require these advanced readout modes. In general, just different readout modalities like global shutter or being able to read out a strip of pixels. The speed, the maximum frame rate, that's also for some of our applications quite important. So we're also excited that there, at least I have the impression there's still a push to increase the readout speed for a small region of interest, or interesting in the sCMOS, if you scale it just in one dimension down, you can still in the other dimension cover quite a wide width of pixels. You typically, what we like is if you can approach like a kilohertz frame rate with maybe 128 or 256 wide pixel strip, or at least approaching it. For some light sheet techniques, sometimes you end up that you actually want to read out very fast a narrow pixel strip, maybe again in the range of 100 to 200 pixels. And if that can be in the future improved, to even faster speeds, some of the cameras we currently use, if you shorten the exposure time below 1 millisecond, you no longer gain much in frame rate. You shorten what you expose the pixels, but you essentially become dominated by the readout time or the pixel clock rate. But if that can be further improved, that would be very exciting, and is also for certain applications an attribute in a camera that we would appreciate. If a camera can handle many regimes from dim to very bright, that's always a bonus. So yes, indeed, certain applications will be performed in very low light settings where you have to be very gentle, but there are also samples that are blazing bright that can exist. So you can think of, if you want to study the morphology of cancer cells and how they change, we can, for example, fill them with a cytosolic marker, and it fills just the entire cells, and we can segment the cells and get the shapes. And that tends to be really super bright, and so you can go fast and still have a reasonably high signal. Or if you don't need to go super fast, you can have really amazing signal to noise and signal rates. And so having a camera that can adapt to that, and, maybe you can change the bit depth if there is a gain in readout speed. If you go with a lower bit depth, then that's a flexibility that is appreciated. There is really a fact that or a tendency that light sheet microscopes are tailored to a certain application. So if you have a light sheet that image embryos, it will, or really large stuff, it will not necessarily be the system of choice if you want to study single cells. But nevertheless, having some versatility, at least in the detection, so that, you know, one system would just not only be a high-speed system and the other, you know, would be short-handed in going fast, that could at least help to limit the number of systems, you know, you would need. So I think that is a daunting thing for any microscope facility, because when users say, hey, I want a light sheet, there's not just one light sheet. They're essentially maybe looking at 2 or 3. And so at least if the cameras have the versatility, so when sCMOS, you know, that could help. But there are multiple avenues where we are excited, or we have high hopes. I still think something that could become really big is really the tissue clearing, and the fact that in principle, if the clearing is really good, then you can achieve subcellular resolution in the tissue. So that prospect is very exciting, because you could all of a sudden study plasticity of cells, be it cancer cells that metastasize different organs, or being plasticity in the brain. You could all of a sudden do things that were unthinkable, and with a certain throughput. The challenge is that if you, even with light sheet, if you go just with the highest resolution, you will, you know, quickly overwhelm any data storage unit. So, but what we think is important is some sort of multi-scale approach that you say in the future, if you could image, say, a whole mouse, if you can clear it, that it becomes optically accessible. You don't want to image the whole mouse at 300 nanometer resolution or higher, because that simply, there is no storage space at the moment. So you would probably want a system that can efficiently image the whole thing at maybe a cell level resolution, or maybe even coarser, and then automatically decide where are the features that need to be imaged at high resolution. Because by hand, some of the work we have done, and some postdocs in my lab have done heroic work, is even a smaller part of the mouse, say just the bone marrow in one of its leg bones, you get completely lost finding certain cell types. And if you do that by hand and go in there and want to image at high resolution, maybe 20 or 100 representative cells of that type, it's just enormous work. So I think having some smart microscopes that can make decisions on their own and can cross spatial scales, that is something where I think light sheet microscopy could become even more powerful there's this currently still unlocked potential that we could essentially study diseases on a whole organism scale, yet one could still get down to the subcellular level. I still also have hope that we could make light sheet microscopes more generic and more easily adoptable by microscope facilities. So, and also make them more user-friendly. So an important aspect, I haven't talked in my slides about it, is I think these single objective or oblique plane or scape type systems, they hold great promise. In principle, you could build them, since by virtue they only use one objective, you can in principle build them around a conventional microscope body. So if one would succeed in making that would turn light sheet microscopy from you have to buy a whole dedicated system and then it can only do that, to something like you could add a module to your microscope, like you have a turf slide or a turf module, you can, in principle, on a certain port, add a light sheet module. There's still work needed to really fulfill on that promise, because there are some caveats to this kind of doing light sheet with just a single objective at the sample end that still need work. But in principle, if some of the engineering and the scientific challenges are overcome, then this could maybe democratize light sheet microscopy even more. So that would truly be helpful. And some of the techniques that were developed for normal light sheet microscopy can be translated over to the single objective light sheet world. So the DSLM works. The ASLM we have tried, but it hasn't worked that successfully yet, because there's still an advantage if you have two separate objectives. You can design them that, say, the objective that launches the light sheet has a certain numerical aperture or certain reserves on angular range, and that falls a bit away of the single objective. So it's a bit harder. I would say it might not be possible to get isotropic resolution. That still is something where having these two objectives is clearly needed, so that you essentially can focus the light sheet down to a similar level as your lateral resolution. But actually, in fact, the structural illumination microscopy and the single objective light sheet, they go surprisingly well together. They actually enable something that is even easier to implement that way. Without going too much into details, in the classical way in which structural illumination is done, you illuminate your sample with a one-dimensional interference pattern, and you have to phase step that pattern, but you also have to rotate it by typically 120-degree steps. That is simply due to the fact that the resolution gain is along the pattern vector. So if you have a stripe pattern like this and the vector goes this way, then the additional aliasing of information happens in that direction of the pattern vector. And so if you want to improve the resolution isotropically laterally, you have to rotate that pattern. That is not too hard to do in a normal SIM microscope, but in a light sheet it becomes kind of hard. If you were to launch the light sheet from the side with one objective, to rotate it, you would have to turn the illumination objective around, or you would have to have three separate illumination objectives, which in either case would be a bit a nightmare to build, or it would make the microscope really complex. And surprisingly, with the single objective light sheet or the oblique plane light sheet, it's essentially a light sheet comes out, if this were the objective, light sheet comes out at an oblique angle, and you can actually rotate that plane azimutally at will. You can think of like a rotating turf illumination does something similar. It essentially just scans the laser spot in the pupil in a circle. And you can actually also do that for the light sheet. And you can also make interfering light sheets that rotate. You don't run out of angular range. And so it might be that actually the single objective light sheet for certain modalities like structural illumination are actually easier to marry or to combine different modalities. I think cameras, speed-wise, at least in light sheet, we could still often go faster than what the cameras allow. So I'm still hoping that either by even more parallelized readout of the camera pixels or by better readout electronics, that speed can be boosted even further. Also, chip size is something I don't think has reached the limit. So cameras may approach, even for advanced objectives and tube lenses, the limit of what can pass through the optics, but you can still multiplex more onto the camera. You can multiplex colors on different portions of the camera. So if you just have one large camera, but you can also multiplex other information. For example, example, spectral information can be multiplexed. There have been ideas how to do that on cameras, on a single chip, in a two-dimensional sense, have a spectrometer. Maybe there are clever ways of multiplexing the different phase steps of a structural illumination pattern onto different portions of the camera. Or we have also recently developed a projection technique that can kind of map a 3D volume onto a single exposure in a light sheet format. And it tends to emulate what a different rotation and then projection would look like. It has the effect that it stretches out the image a bit. So it actually would be helpful if the camera is, at least in one dimension, larger than the field of view that the system can support, because when we create these different views or projection of the sample, we stretch the resulting image out. So also there, larger cameras would be helpful. Lastly, one area that also would be important is to improve the wavelength range of cameras, so that you could, for example, go into the near infrared or even beyond. So for many intravital imaging studies, it would be great if we could get to kind of certain absorption windows that exist in the near infrared at 900 or 1300 nanometer, and potentially that could enable deeper light sheet imaging. There are still challenges in having probes that also work at that wavelength range, but I think if this becomes a viable avenue of fluorescence imaging in that wavelength range, then that would be very exciting, and the camera technologies also would need to, all the things we enjoy in the visible on CMOS cameras, if they could be translated to the near infrared, that would be great.
Many thanks to our guest speaker, Professor Reto Fiolka, for providing his expertise and some great context surrounding scanning light sheet and the light sheet landscape in general. For the next part of this webinar, I'd like to talk about camera technologies and how they can serve scanning light sheet. As Professor Fiolka mentioned, the rolling shutter is vital, as well as the concepts of multiple rolling shutters or multiple regions, adding to the power of light sheet through parallelization. So what does a camera for light sheet need? A camera for something like scanning light sheet should avoid compromise and feature best-in-class specifications from each of these major areas. First is sensitivity. If your camera isn't sensitive enough, you simply won't be able to see your sample at lower light levels, and you won't be able to answer any of the scientific questions you're asking. And sensitivity here is mainly controlled by minimizing the sources of noise and maximizing signal collection or quantum efficiency. Another aspect of high sensitivity is the ability to lower the camera exposure time and therefore increase the speed. We have researchers using our cameras to perform calcium imaging of large samples in a light sheet across a whole volume, or voltage imaging in brain samples. These both require high-speed imaging to capture dynamic activity, but they need sensitive cameras in order to image at these very low exposure times, often just a couple of milliseconds. Throughput is also vital. Light sheet is often used of larger samples. A camera with a large sensor will have a large field of view and a small pixel, which results in high-resolution imaging, especially if you match it with a suitable objective. So the combination of a very large sensor and a very small pixel will result in the ability to image large samples at a subcellular resolution at a variety of different magnifications. The ability to differentiate between high and low signals is also important. This is known as the dynamic range, and it allows you to suit the camera to the sample signal level that you're expecting from your image experimentation. Finally, as well as the major camera specifications, it's important to have special features and flexibility in software and hardware. The three I'd like to highlight here are programmable scan mode. This is how we can control the camera rolling shutter for scanning light sheet applications. The ability to form multiple readouts or regions for parallelization. And even the ability for advanced hardware triggering to further synchronize light sources to the camera, or vice versa, and increase imaging efficiency. So there are three main cameras I'd like to talk about at photometrics that are suited for this. The first is, as you can see, the Kinetics. We also have the Prime BSI Express and the Iris 15. And I'll go over these cameras in this order. The Kinetics is the next generation of a CMOS camera. It was designed to push the boundaries of what a CMOS can do for research. In general, the Kinetics is much faster, with a much larger sensor and lower noise levels than a typical CMOS camera. With the Kinetics, there's no need to compromise. So if you can compare it to a typical 18mm CMOS, the Kinetics has over 8 times the imaging speed. It can capture the most dynamic samples at thousands of frames a second, great for techniques like voltage imaging. The Kinetics also has a sensor that's over 2.5 times larger. This results in a huge field of view and very high throughput imaging, and the ability to capture more data in every frame. Along with all of this, the Kinetics also has remarkably low read noise, down to less than 1 electron. This results in high sensitivity for imaging even the weakest of signals. The Kinetics has been around for several years now and has been a huge hit with the light sheet community. It's being used for various static, scanning, functional, single objective, and oblique plane light sheet imaging setups all across the globe. The reasons for this are manifold. We'd like to talk about the field of view and the speed in particular. Firstly, the field of view. The Kinetics sensor is 29mm in its diagonal. This is 2.5 times larger than a typical CMOS camera. Here we can see in the image, you have an EMCCD in the middle, around 11mm. Typical CMOS comes out at around 18mm. The Kinetics 22 and the Kinetics are both large form factor cameras, so they go at 22 and 29mm. Because it's 2.5 times larger than the typical CMOS camera, you get 2.5 times more data in every single frame, so it's much higher throughput. You don't have to do so much scanning or tiling. Every image simply contains more information. Because you can image more of your sample with less acquisitions, your experiments can become far faster and your sample gets far less light dose. Or, if you don't need the extra field of view, you can also pair it with a splitter. We work very closely with companies that produce image splitters. Essentially, you can split the square sensor 2, 3, or even 4 times, and you can image separate wavelengths, separate Z-planes, separate polarizations on each section. So if you don't need the full 29mm of the Kinetics, you could still image something like 4 wavelengths simultaneously with a 15mm wavelength, because you'd occupy each quadrant of the camera. This allows you to be extremely high throughput and avoids things like waiting for the filter wheel to change. You could just image the wavelengths all at the same time. We also offer the Kinetics 22. If you won't be using a splitter and your microscope doesn't have a very large maximum field of view, the Kinetics 22 is 22mm in the diagonal. It's essentially optimized for microscopes or systems with a smaller maximum field of view. It's still larger than the typical CMOS, about 40% larger, but it's more optimized towards these systems. Having a big field of view is typically a really big deal for microscopy, however. So in this example, we can see a large tissue sample imaged with a typical CMOS. Each image has 3 different wavelengths and has about a 15% overlap with its preceding image, so there's less tiling artifacts. So this XY scan with the overlap and the 3 wavelengths took 25 acquisitions, and this is going to be a fairly long imaging experiment. With the Kinetics, however, it takes 9 acquisitions to image the same area. This is over 3 times faster to image, requires far less light dose to your sample, and if you expand this over many experiments and research projects, the larger sensor in the Kinetics really saves significant time to your work. And you can go to your lunch break much earlier. A real-life example of this is with Professor Ulrich Kubitschek at the University of Bonn. Professor Kubitschek is doing light sheet with expansion microscopy. So expansion microscopy is where you physically magnify your sample by enlarging it for super resolution imaging. This means it is several times larger in volume, and you need a suitably large camera in order to image at this kind of size. So the kinetics is an ideal solution here. You can see in tile A, it took a typical CMOS 10 acquisitions to capture this area, whereas the kinetics, it took 2. And you can see from panels C and D, this is all happening at very high resolution with high magnification. So just by increasing the field of view of your camera, if your microscope is able to image across that size as well, you can drastically improve the efficiency of your imaging, especially for light sheet. As Professor Kapicek also mentions in the blue box quote, the signal to noise ratio is excellent, so the high sensitivity also really helps it. The other standout benefit of the kinetics is the speed. So in the speed mode, the kinetics will image at 500 frames a second across this large 29mm field of view. This is 8 times faster than a typical CMOS camera if you regioned the kinetics down to 18mm. And so with such a fast camera, you'd really be able to see what you're missing in the gaps, and you can capture highly dynamic samples. And because this is CMOS technology, every time you reduce the number of rows, you increase the speed. So if the full frame goes 500 frames a second, reducing it to half the size will go at 1,000 frames a second, and then 2,000, 4,000, and so on. Because there's a readout node for every column, you always get the full width for free. So you essentially end up with a letterbox region format, which can image at extreme speeds. And this is well suited to long, thin samples that often occur in light sheet, such as zebrafish, nematode worms, fibers, and lots of neuroscience imaging with neurons. Once you squeeze down below 30 rows, you can get to really extreme high speeds. Here you can see it goes over 100,000 frames a second, or 100 kilohertz once you get to several rows. This really lets you see what you're missing in your sample, and is only possible due to the high sensitivity. In order to image at 1,000 frames a second, the kinetics has to expose for 1 millisecond. It can only do this if it's sensitive enough to see the sample. The production of so many frames would also result in huge file sizes, but as our speed mode is an 8-bit mode, files produced using the speed mode are half the file size as the other 12 and 16-bit modes. Here you can also see, compared to a typical CMOS, in order to image at 500 frames a second, you'd have to achieve this kind of region with your typical CMOS camera, versus the kinetics achieving this kind of field of view. So you not only get a higher speed, you get a higher speed across a larger area. So here we can see the kinetics in the speed mode would image at 500 frames a second across an 11 times larger area than the typical CMOS camera. So not only do you get a high speed, you get a high speed across the very large field of view. As well as the kinetics, we also offer the Prime BSI Express. This is a compact, powerful CMOS camera that images with high sensitivity and high speed, all with a small form factor. So with the Prime BSI Express, you can image up to 95 frames a second across the full frame with 1 electron of read noise. This is another popular choice for light sheet, and the Prime BSI Express has been used for a variety of light sheet applications. The Prime BSI Express is easily integrated into existing systems or OEM devices, and has proven to be an ideal solution for the majority of imaging applications. And for any applications where greater speed, larger sensors, or lower read noise are required, the Kinetics family are available. For everything else, there's the Prime BSI Express. Some examples here. This is an application using OpenSPIM with the Prime BSI Express from Dr. Franziska Kurt of the University of Oldenburg. They needed a camera to image whole cleared zebrafish, particularly the brain. The Prime BSI Express here is ideal for high-resolution light sheet imaging. It's able to capture the whole fish brain without sacrificing image detail. And as Dr. Kurt says, the Prime BSI Express is a big advantage. For another example, we have Professor Fiolka's work with ASLM, where the Prime BSI Express was used again in a whole cleared zebrafish, and you can see this image here is color-coded for Z depth. So the small pixel is ideal for this high-resolution imaging across the scanning light sheet application. And as Professor Fiolka mentions, the Prime BSI Express is reliable and pairs well with his imaging techniques. The final product we're featuring here is the Iris 15. This camera is designed for large field of view, high-resolution imaging. So while the kinetics in the Prime BSI Express have a 6.5 micron pixel, which is optimized for Nyquist with higher magnifications like 60x, the RS-15 has a 4.25 micron pixel, and this is therefore better optimized for resolution at lower magnifications such as 40x or less. So the small pixel combined with a large 25mm field of view sensor results in a 15 megapixel array. Essentially, the RS-15 is ideal for imaging larger samples at higher resolutions, especially in light sheet. The fact that it's a rectangular sensor also pairs up well with microscope objectives. So the combination of the large field of view with the small pixel really boosts resolution here. So you're aiming for subcellular resolutions across large samples at low magnifications. It's been used very widely in light sheet applications and is available also in a 9 megapixel model, the IRIS-9. For a great example of the RS-15 in action with light sheet, we turn to Dr. Fabian Voigt of the University of Zurich, who is a developer of Mesospim, which is a mesoscale light sheet application for imaging large centimeter scale samples beyond the microscale, such as mouse organs, including this image here of a cleared mouse brain. The RS-15 in particular is an ideal solution for Mesospim and other large sample light sheet applications. The rectangular sensor is well optimized for this format of imaging. So that's the three product families we're featuring here. And we can briefly go over the specifications, and this is for your reference. The Kinetics family cameras have a very low read noise, high QE, balanced 6.5 micron pixel, and very large fields of view at a very high speed. The Prime BSI Express has, again, high speed and low noise. And the RS-15, the main takeaway here is the smaller pixel across, again, a very large sensor. So all these cameras are well suited for light sheet, not only because of these standard specifications, but because they all have programmable scan mode, which is ideal for light sheet, particularly scanning light sheet. But what on earth is programmable scan mode? This is our method to give additional control over readout to researchers. This includes modification of both scan timing and or scan direction. So for scan timing, there's two control approaches. There's line delay and there's scan width. Line delay does exactly what it sounds like. It allows you to add a delay to either end of the readout process, effectively allowing you to choose the line time. And this can synchronize with the scan time of your beam across the camera sensor. If you need to slow down the readout of the camera to match with your beam, you can use line delay to do this. The other option is scan width. This allows you to choose the number of rows in the active part of the readout between the readout and the reset signals. Again, this allows you to optimize the camera readout to the thickness of your light sheet or pencil beam and how many pixel rows that's going to take up. So you control the width of the readout and you control the delay timing. This allows you to really synchronize up to the beam and minimize any dark time, making the imaging more efficient. As well as scan timing, there are controls for scan direction, namely down, up, and down, up. These titles refer to the direction of the camera readout. So the typical mode of the camera is down. This basically means the camera reads out from the top of the sensor to the bottom, so it reads down the sensor. This can be inverted in up, where it reads from the bottom of the sensor to the top. But the real power is in down, up. So this allows the camera to read out from top to bottom and then from bottom to top. So there's no need to reset the readout or your light sheet beam at the top of the camera. You can just scan it to and fro, up and down. This minimizes dark time and further increases efficiency. The triangles here represent the images, while the triangles in down up are upside down in every other image. The camera knows what it's imaging, and when these images are output, they're all in the same orientation. You just get the ability to image with both sweeps of the readout going up and down. So overall, this makes programmable scan mode a very powerful piece of software for our CMOS cameras, and makes certain light sheet modes possible due to the ease of synchronization with the beam, even with different beam speeds, widths, or directions. As well as programmable scan mode, we have some modes unique to the Kinetics. Because the Kinetics has a powerful FPGA processor on board, we can program and implement new modes into the Kinetics cameras as time goes on. And one of the modes we've implemented relatively recently is multi-ROY. So if you're doing parallelized scanning light sheet, such as parallelized DSLM, as Professor Fiolka mentioned, having multiple regions of the camera that can read out are advantageous. So you may want to image at high speeds, but not across the entire sensor. If you have this image on the right here, you may want to image just the areas those 3 red squares are. If you just establish one region around them, you'd have to read all the way through it. If you can establish multiple regions, you can image these areas at higher speeds. And this is what's known as multi-ROY. Existing region of interest behavior is essentially limited by bounding box constraints. If you want to image those 3 regions on the left, you would establish a region like so, and it would be very fast imaging. However, if you have the situation on the right, where one of your regions is offset, you'd have to scan everything from top to bottom within that red box, and this would limit the speed. So the difference between a small and a large bounding box effectively controls the speed of the readout, because it has to read all the pixels in between your desired areas. The solution here is multi-region, where you can simply establish one region around one set and one around the other set. The camera skips the readout in between them, and it massively improves the imaging efficiency. So you get faster sampling, less data because you've skipped the rows in between. You can precisely analyze specific sample regions. And you could use this with all sorts of scanning beams if you have multiple light sheets. So you could have light sheets imaging each one of these 3 orange zones here, and they can scan up and down, with the further potential to even have multi-readout or even multi-programmable scan mode. So in summary, light sheet and scanning light sheet are highly versatile, and this is why these imaging techniques are evolving so rapidly. CMOS cameras with very large sensors and very high speeds present high throughput solutions, and modes such as programmable scan mode allow for advanced readout control, allowing you to synchronize the camera's readout with the scan of your light sheet. This is most exemplified in the Kinetics family with things like multi-ROY, and indeed there is no need to compromise with these advanced scientific CMOS cameras. Thank you very much for listening to this webinar. Please feel free to head over to our website, www.photometrics.com, where a lot of this information is also contained, and you can see other examples of customers using our cameras for light sheet applications. If you have any questions, I'd love to answer those now.
Thank you, Matthew and Professor Fiolka, for your informative presentations. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located in the far left of your screen. We'll answer as many of your questions as we have time for. Let's go ahead and get started. Our first question that we have today asks, what are the typical operating wavelengths for DSLM and ASLM, and how important is the 850 to 1150 nanometer range?
Great question. In general, in terms of light sheet and scanning light sheet, you mostly have people using the wavelengths where the camera is most sensitive and where they have the fluorophores. So we have a lot of people using the 400 to 700 range. There's no reason why they can't stretch out closer to the near infrared. The cameras are sensitive all the way down to, I believe, 1100. But you'd need to accommodate your light source for the light sheet there. So I think some of the work we have people doing is with long wavelength light sheets, so for the greater penetration. But I think most of the work is done between I'd say 400 and 600. This is also where the camera is most sensitive. The peak of sensitivity is 550. You know, you get the nice sort of dappy, fitsy, tritsy tricolor fluorophores right along that way. So you get the maximum sensitivity too.
Wonderful. Thank you. Our next question that we have here asks, are there any other useful light sheet modes coming to photometrics cameras?
Another good question. I'd say you just heard about programmable scan mode and multi-ROI. In general, the processor on the camera is quite powerful. So in theory, you can essentially evolve the readout as the need for it evolves as well. So once we get multi-region readout, there's no reason why we can't also get multi-programmable scan mode. So you should, in theory, be able to do that twice or multiple times across the same camera. And this would be good for things like parallelized light sheets, which we saw parallelized DSLM. Beyond that, there are other things that the camera can do in recent firmware updates with regards to things like frame summing and frame averaging as well, in case you need to look at just the dynamism in your sample and not look at anything that is static. But in general, I think the main benefits for light sheet are the advanced control of the readout. And now that you can do that across the whole sensor, the next step is to see how many more times you can do it across the same sensor. Since the sensors are so large, you can then split them up and have it be parallelized.
Great, thank you. And we have time for just one more question here today. That question asks, what are the benefits of programmable scan mode for light sheet?
Yeah, we went over this in the presentation, but the main benefit here is flexibility. So the whole point is that you have the power of the hardware and you need the flexibility in the software. So the cameras are very compatible with lots of different operating systems, lots of different imaging programs, acquisition software, and this kind of thing. And the last thing you need is for it to be compatible with your hardware. So you need to, hardware trigger to your light sources, but then you need the camera to be able to adapt to, oh, my light sheet is faster than this, my light sheet is slower, it's wider, thicker, in different directions, different shapes, this kind of thing. So the main benefits of programmable scan mode are the ability to then match it to the kind of imaging that you're doing. So if you've got a very thick light sheet that moves very slowly, you can establish a thick readout and reset banner, which then moves at the speed you want it to. And this then minimizes the dark time and maximizes your efficiency.
Great. Thank you again, Dr. Matthew and Professor Fiolka, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Teledyne Photometrics, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions that we did not have time for today, and those submitted during our on-demand period will be addressed by our speakers via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Goodbye.
Thank you, everyone. Goodbye.